In this presentation, I will be looking at mathematics from the 1600s to the 1800s. There's a lot of great discoveries during this time frame. Too many, in fact, for me to touch on everything. So I've compiled a list of what I considered to be the most noteworthy. So let's begin. As you can see, I've created a timeline of notable mathematicians of this time frame. I will stop on each one and share some of their discoveries that they have contributed. First off is Johannes Kepler. Kepler was a German mathematician and astronomer who discovered that the Earth and planets travel about the Sun in elliptical orbits. He gave three fundamental laws of planetary motion. He also did important work in optics and geometry. In 1609, he publishes Astronomia Nova, or New Astronomy. This work contains Kepler's first and second law on elliptical orbits, but only verified for the planet Mars. Next on our journey through time is Galileo Galilei. Galileo was an Italian scientist who formulated the basic law of falling bodies, which he verified by careful measurements. He constructed a telescope with which he studied lunar craters and discovered 4 moons revolving around Jupiter. He was also a Copernican scholar. In 1610, Galileo publishes Sidereus Nuncius, or Message from the Stars, which describes the astronomical discoveries he has made with his telescopes. In 1632, Galileo published Dialogue concerning the 2 chief systems of the world, Ptolemaic and Copernican. Briefly, the Ptolemaic system had the Earth at the center with all the planets and Sun moving around the Earth, while the Copernican system suggests the Sun was the center and all the planets orbited the Sun. The Inquisition banned the sale of his book and ordered Galileo to appear in Rome before them. He was sentenced to life in prison. The sentence was carried out somewhat sympathetically and amounted to house arrest rather than a prison sentence, but nevertheless he was imprisoned for the remainder of his life. Moving through time, we come to Pierre Fermat. Fermat was a French lawyer and government official, most remembered for his work in number theory, in particular for Fermat's last theorem. He is also important in the foundations of calculus. In 1647, Fermat claims to have proved a theorem, but leaves no details of his proof since the margin in which he writes is too small. Later known as Fermat's last theorem, it states the equation x to the n plus y to the n equals z to the n has no non-zero solutions for x, y, and z when n is greater than 2. This theorem is finally proved to be true by Wiles in 1994. Moving along, we come to René Descartes. Descartes was a French philosopher whose work La Géométrie includes his application of algebra to geometry, from which we now have Cartesian geometry. His work had a great influence on both mathematicians and philosophers. Moving along, I'll speak quickly on Florimond Debaun. Debaun was a French jurist and amateur mathematician who produced the first important introduction to Descartes' Cartesian geometry. In 1649, Debaun writes a brief which contains the many results on Cartesian geometry, in particular giving the now familiar equations for hyperbolas, parabolas, and ellipses. Continuing on, we'll stop at Blaise Pascal. Pascal was a very influential French mathematician and philosopher who contributed to many areas of mathematics. He worked on conic sections and projective geometry, and in correspondence with Fermat, he laid the foundations for the theory of probability. In 1654, Fermat and Pascal began to work out the laws that govern chance and probability in 5 letters which they exchanged during the summer. Also in 1654, Pascal publishes his treatise on the equilibrium of liquids on hydrostatics. He recognizes that force is transmitted equally in all directions through a fluid and gives Pascal's law of pressure. And our journey continues to Robert Hooke. Hooke was an English scientist who made contributions to many different fields, including mathematics, optics, mechanics, architecture, and astronomy. He had a famous quarrel with Newton at one point. In 1660, Hooke discovers Hooke's law of elasticity. Continuing our journey through time, we come to one of the most famous mathematicians, Sir Isaac Newton. Newton is generally considered the greatest English mathematician of his generation. He laid the foundation for differential and integral calculus. His work on optics and gravitation make him one of the greatest scientists the world has ever known. In 1665, Newton discovers the binomial theorem and begins work on differential calculus. In 1687, Newton publishes the Principia. In this work, recognized as the greatest scientific book ever written, Newton presents his theories of motion, gravity, and mechanics. His theories explain the eccentric orbits of comets, the tides, and their variations, the precession of the Earth's axis, and the motion of the moon. When speaking of Newton, Gottfried Leibniz should always be noted. Leibniz was a German mathematician who developed the present-day notation for differential and integral calculus, though he never thought of the derivative as a limit. His philosophy is also important, and he invented an early calculating machine. In 1673, Leibniz demonstrates his incomplete calculating machine to the Royal Society. It can multiply, divide, and extract roots. In 1675, Leibniz uses the modern notation for an integral for the first time. In 1676, Leibniz discovers the differentials of basic functions independently of Newton. In 1677, he discovers the rules for differentiating products, quotients, and the function of a function. In 1679, he introduces binary arithmetic, although it wasn't published until 1701. And finally, in 1684, Leibniz publishes details of his differential calculus. His book contains the familiar D notation and the rules for computing the derivatives of powers, products, and quotients. We continue to traverse through time and stop at a family dynasty of mathematicians, starting with Jacob Bernoulli. Jacob was a Swiss mathematician who was the first to use the term integral. He studied the catenary, the curve of a suspended string. He was an early user of polar coordinates and discovered the isochron. In 1691, Jacob invents polar coordinates, a method of describing the location of points in space using angles and distances. And now we will look at his brother Johann Bernoulli. Johann was also a Swiss mathematician who studied reflection and refraction of light, orthogonal trajectories of families of curves, quadrature of areas by series, and the brachistochrone. In 1694, Johann discovers L'Hopital's rule. Continuing on, we have to stop at Johann Bernoulli's finest pupil, Leonhard Euler. Euler was also a Swiss mathematician who made enormous contributions to a wide range of mathematics and physics, including analytic geometry, trigonometry, geometry, calculus, and number theory. In 1735, he introduces the notation f of x. In 1736, Euler publishes Mechanica, which is the first mechanics textbook which is based on differential equations. In 1748, he publishes Analysis Infinitorum, which is an introduction to mathematical analysis. He defines a function and says that mathematical analysis is the study of functions. Moving along, we come to Robert Simpson. Simpson was a Scottish mathematician best known for the Simpson line of a triangle, even though he was not the first discoverer of it. In 1753, Simpson notes that in the Fibonacci sequence, the ratio between adjacent numbers approaches the golden ratio. And now we'll take a quick look at Franz Aepinus. Franz was a German scientist who did important work on electricity and magnetism. In 1759, Aepinus publishes an attempt at a theory of electricity and magnetism. It is the first work to develop a mathematical theory of electricity and magnetism. Our journey through time is nearing the end, but next up is Joseph Louis Lagrange. Lagrange was an Italian-born French mathematician who excelled in all fields of analysis and number theory and analytical and celestial mechanics. In 1785, he begins work on elliptical functions and elliptical integrals. In 1788, Lagrange publishes Analytical Mechanics. It summarizes all the work done in the field of mechanics since the time of Newton, and is notable for its use of the theory of differential equations. With this work, Lagrange transforms mechanics into a branch of mathematical analysis. Our journey has come to an end with our final stop at Carl Gauss. Gauss worked in a wide variety of fields in both mathematics and physics, including number theory, analysis, differential geometry, magnetism, astronomy, and optics. His work has had immense influence in many areas. In 1799, he proves the fundamental theorem of algebra. All of his other contributions are out of the timeline we are looking at. So that concludes my look through time of mathematics from 1600 to 1800. My name is Bradley Moore, and this was a presentation for the History of Mathematics, Mayville State University. Thanks for watching.